Hello everyone, my name is Peter and my third year project aims to create two very different systems. One that recognizes visual symbols and another to control the movements of two humanoid robots. While these don't seem particularly connected at first glance, the driving desire behind both of them is to use biologically inspired technologies to implement them. As a result, both of them have been created using a neural simulator which mimics the behavior of mammalian brains by simulating the activity of groups of interconnected spiking neurons while also running on hardware which matches the brain's organization. The system that I have designed and implemented using spiking neurons controls the arm movements for a pair of robots part of an art exhibition at the Manchester Art Gallery. The idea of the art piece originated from a Swedish artist who collaborated with a team of Swedish mechatronics students in order to build the robots at KTH Stockholm. They sit in their chairs discussing the nature of consciousness and identity by following a predefined script but may be interrupted by onlookers and will react by telling them to be quiet or go away. Scope of the project was to imbue the robots with human-like gestures by raising arms in the air when silencing the audience and gesturing naturally while talking. In order to achieve the desired behavior, I have engineered a network consisting of interconnected groups of neurons. On screen is the full network controlling the robots at the gallery, presented in an interactive user interface. At the bottom of the screen lay the simulation controls with speed of simulation compared to real time, the current time of the simulation, a history controller which affects how much previous information is presented on the output graph, and the start and stop button. On the left are the inputs to the simulation. Their only use is to be able to interact with it, they do not have a biological counterpart. Outputs are on the right, while in the middle we have several groups of neurons interacting with each other. This area can be treated as a black box which executes one of three predefined actions with either one or both of the arms. When the simulation starts, the default action is action 1, which means that the robot is gesturing. For this action, the basal ganglia and thalamus models cooperate to inhibit the neural populations representing the arm positions needed to silence the audience. This means that the trajectory computing system will take the sound signal, in this case an artificial sinusoid, and a base position and compute the path to be taken by the robotic arms so as to accomplish a gesturing movement while they speak. Furthermore, the system selects a random arm to use for gesturing whenever the robots move on to a different sentence. This is accomplished by using a direction selection subsystem relying on computing the dot product between the input vector and two predefined orthonormal vectors representing the left and right directions. The result of applying the two operations is that we now know the angle between the given and both of the predefined vectors, thus we can make a decision upon which arm to use. Finally, in an analogous fashion to gesturing, the system can also allow the robots to silence the audience or simply idle while not talking. Silencing is done by raising one or both of the arms in a predefined position with the hand close to the mouth, and the idling is done by keeping the arms still at the base position. As a starting point for the vision system, I have created a simulation which uses the dynamic vision system equipped on a pushbot in order to follow flashing light. This is not a standard camera which operates at a fixed refresh rate. It operates similarly to a biological retina with changes in local brightness represented as spike trains. This behavior is achieved by implementing a winner-takes-all network based on mutual inhibition. In other words, each region of the receptive field excites or pulls into one of 9 corresponding groups of neurons, and each of these inhibit all the others except themselves. Each group of neurons, also called a population or ensemble of neurons, have a recurring connection so as to offer them a form of memory. This network will have the effect of selecting the population which encodes the largest value, while all the others are inhibited, thus driving the motors in the direction of the region with the highest brightness. This approach ignores any shape information, relying exclusively on the brightness of the flashing LED. It would be a lot more interesting if the pushbot would react to symbols or shapes rather than purely on light intensity. To this end, I have trained the population to react preferentially to a bar of a particular orientation, represented by a Gabor filter. The output of the network is a value representing the confidence that the input filter is at the preferred orientation. Placing 4 of these groups of neurons trained to react preferentially to a different orientation bar into the same network and selecting the one with the highest output, we have created a system that can provide edge detection for a relatively small area of the receptive field. However, if we consider that we want to create a simulation that is biologically plausible, we need to be able to scale it up and also use plausible structures from within the visual cortex. Thus, the basal ganglia used previously for selecting the most likely orientation is removed and replaced with a winner-takes-all network. The model used is a hierarchical, feed-forward network represented here only in its first layers, but sufficiently deep to be able to extract some basic behavior. The behavior we have now imbued into this network allows a pushbot to respond to simple symbols, to advance or retreat based on the dominant orientation in the scene. This was an immensely interesting and demanding project with deliverables which accomplish robotic motion control and some basic symbol recognition using the neural engineering framework's precepts, the Nengo simulator, the biologically inspired silicon sensor retina, and the Spinnaker neuromorphic computation platform. Thank you for watching this very high-level whistle-stop tour of my third-year project.